When the light is emitted from a source, it spreads in the space in all the directions. This phenomenon is described by Huygens wave theory. It says it is a generation of wave fronts. Generation of wave fronts. Generation of successive wave fronts and expanding outward. They expand outward in all the direction at a speed of light. That is what the Huygens wave theory says. Once the wave fronts are generated, they expand outward at a very fast rate at the speed of light. That is, spherical size increases, expanding, and bigger spherical size. Now the question is, when the wavefront is generated, what would be the shape of the wavefront? It depends on the shape of the source of light which emitting that, and also the distance of light source. What are the types of shapes of light sources you can visualize? It is one such case. It is a point source or a small sphere light source. This light is emit, this source emit wave fronts of spherical shape, spherical wave fronts in succession, one after the other, expanding at fast rate. The spherical wave fronts, spherical shells, that is expanding. The shape is spherical in shape. If the source is point source or small sphere. If the source of light is linear shape, like tube light or some other like tube light like structure, then the shape of wavefront would be cylindrical in shape, and cylindrical shape generated in succession one after the other. That is hollow cylindrical shape. Wavefront will increase, expand in size. Cylindrical shape is the wavefront. And one more case, if the light source is at infinite distance and these light rays are come from the infinite distance. In this depiction, we use both the ray optics and wave optics to represent the shape of the wavefront. Here, this will says the shape of the wavefront, and the rays will represent the propagation of wavefronts and the direction. They are always perpendicular to the wavefronts. These rays always perpendicular to the wavefronts, showing the direction of propagation of wavefronts. When the light is coming from the source at infinite distance, best suited for it. And the reason for this, why they become flame at the infinite distance. As the light travels over a long distance, the large distances, the size of the sphere will increase. It will turn into an infinite size. The sphere size increase, and becomes a size of infinite size. If that is the case, what would be the surface, curvature of the surface? Almost, what is that? Becomes negligible. Surface curvature becomes negligible, and flattens into a plane. That is a flat plane. Originally it is spherical shape, but appears or almost turns into a plane. Curvature becomes negligible. So we can write this diagram. Planar wavefronts. And one more concept is important from the point of examination. Here, when light passes through some optical instruments like convex lens, concave lens, or mirrors or prism, is there any change in the shape of wavefront? If so, what is that change? See, there is a change, and see what is the kind of change taking place. Let us consider a convex lens. Is a convex lens, as you know, as the light passes through the convex lens, the rays converge to a point. There is a focal point of the convex lens. All rays converge to a point. In this case, the shape of wavefront, it is planar before passing through, because it ray coming from the infinite source. Planar. Once it passes through the convex lens, the wavefront changes into spherical shape like this. Not planar. Planar into spherical shapes like this. And these spherical shapes converging towards the point. What is meant by converging? The shapes shrinks. The size shrinks as the light moves closer to the point. You are shrinking and shrinking to the point. Finally, spherical shape. The spherical shape shrinking. Converging spherical wavefronts are generated after passing through convex lens. Then, what is the case for concave lens? In case of concave lens, as you know, as the light passes through the lens, the light diverges from this point. Appear to diverge from this point. This is the focal point of convex lens. Appear to diverge. Then what is the shape change? The planar shape of wavefront changes into again spherical shape. Once they come out, the shape changes into spherical shape like this, spherical shape like this, spherical shape like this, and they are expanding. Here the wavefronts are diverging away from this point, expanding away from this point. The shape is spherical but diverging away. Here the shape is spherical, converging to the point. That is the difference. After the light emerging from these wavefronts are like this. Diverging wavefronts, spherical wavefronts, changes from plane to spherical shape. And another that is optical instrument, that is a concave mirror. It is a mirror, concave mirror. As you know, when the light after reflection from this surface, the light rays converge to a point, again focal point of the mirror. That is a focal point of the mirror. In this case, here the incident light are planar wavefronts progressing toward this. After the incident, that is reflection, changes into again spherical shape, spherical shape, spherical shape, spherical shape. What kind of spherical shape? Converging wavefronts. That is, the size shrinks to 0 here. Converge to point. Converging wavefronts. Converging spherical wavefronts are generated after reflection. That is a change in shape. And what is the case when the light passes through a prism like this? Planar, before passing through. After the light rays passed out, again planar. The size remains same, the size shape remains same, planar. What is the difference is that the planes are tilted are rotated slightly downward to the base of the prism. Here the planes are straight, here the planes are tilted or slightly rotated downward. The reason here, the velocity of light decreases while it is passing through prism, the glass. That is the reason tilting downward. So this is a few examples. We have realized the change in the shape of the wavefront after the passing through some optical objects like this. The next question is the law of reflection. Recall the law of reflection in accordance with the ray optics. This is the ray optics. Here, the plane of surface on which light is reflecting. Light in this angle of incidence, here in this angle of inclination with the surface, it is an incident ray, it is a reflected ray. And this ray is normal to the surface at this point of incidence. That is perpendicular to the surface. This angle is called as angle of incidence. There is angle between this line and incident ray is angle of incidence, and the angle is called as angle of reflection, angle between the reflected ray and the normal reflection. According to the law of reflection, I equals R. Angle of incidence equals angle of reflection. It has already shown. If that is the case, if the wave theory arises, that wave theory should also prove that angle of incidence equals angle of reflection. If you consider wave concept. What is wave concept? For the wave concept, you are taking any two rays, parallel rays like this, enclosing the planar wave fronts. Here the wave fronts are generated successfully and passing or flowing in this direction. And these rays are after reflection, there what is that they propagate in this direction. Remains parallel. Of course, the distance between these two remains same even after reflection. And the planar rays, wave fronts, they are perpendicular to this planar wave fronts. Here they changes like this. These are reflected wave fronts. These are incident before reflection. Incident wave fronts before reflection direction. And this is a wave front I am talking about. We are concentrate on the wave front. This is the wave front. After reaching the surface, this is the surface on which the light is getting reflected. This wave front is always perpendicular to the line like this, and it is an alignment with the surface like this, with this inclination. This is planar. Surface is planar. The angle between this plane and this plane is incident wave front, begins to incident, and the angle is called as angle of incident. After reflection, you see that the wavefront, planar wavefront begins to appear from here. This is the point. No, from here, first reflected wavefront and generates successively like this. And again it is a plane, that is a plane wavefront, planar and this planar. This plane is a reflected wavefront, first reflected wavefront. And the angle between this plane and this plane is called as angle of reflection, according to wave theory. And we have to show that I equals R. You have to show this angle I equals R. This is the law of reflection in accordance with the wave theory. We have to give the proof for this. This is a geometry of wave. What is the proof? It requires the knowledge of geometry. Let us use the knowledge of geometry to prove I equals R. What is that knowledge of geometry? Here, look at this point. This is the incident wavefront touches the surface, but here away from the surface in the air. Here the plane shape is ending, and here the light ray is ending here, and after reflection it is in the progress in this direction. And still the ray at the point propagates till it reaches the surface like this point. And what would be the shape of the wavefront when the light is traveling from this point to this point? Up to this point is flat. Then what is the wavefront? How the wavefronts are generated from here to here, from this point to this point? This question. Here, from this point to this point, it is not planar. They are spherical in shape. What is a spherical in shape? This is a diagram. Let us take this. From this point, the spherical wavefronts are generated. That is the spherical wavefronts generated. What kind of spherical wavefronts are generated? Converging wavefronts. Converges to point P. Here shrinks the wavefront, the size shrink till the point is reaching here. Spherical wavefronts are generated. These are converging wavefronts till the point. So that is the shape of wavefront when the light is traveling from this point to this point. Similarly, when the light ray is reflected from this point, we see the plane only from this point. The wavefront planar is from this point. From this point to this point, how does the light travels in the form of wavefront? Again, spherical shape. Here, the spherical wavefronts are generated from this point. This is spherical wavefronts, point A, generated from this point. Spherical wavefronts are successively generated and are expanding outward. They are diverging wavefronts away from this point till the point is reached. Here, wavefronts are generated. Spherical wavefronts expanding till the point is reached here. From here to here, wavefronts are spherical in shape, expanding from this point to this point. And is successive spherical waves. So like this geometry. And this spherical wave opposes hemispherical. What is hemispherical? Light remains on the surface, incident and reflect, and light is not passing through, that is, pass down the line or surface, not away. So it is hemispherical, of course. What is spherical shape? It is always hemispherical in shape like this. And this is the point where first reflected wavefront arises. This is the point where first incident wavefront here appear. And this geometry, let us expand, that is geometry into this kind of geometry. Where you see that on this point many spherical wavefronts are generated, smaller to bigger and bigger and bigger. When it reaches this point, is highest, that is the one I am taking about. From this point, It is the highest spherical wavefront up to this point. And from year to year, spherical wavefronts converge, decrease in size, where generates highest spherical wavefront. That is the one what I am talking about, the spherical wavefront. From this point, touches with that is a incident wavefront, reflected wavefront. So this is the highest spherical wavefront begins to commence. This is the highest spherical wave ending at this point generated. And these two spherical wavefronts I am selecting are considered. And what are these spherical wavefronts? Are identical, exactly identical spherical wavefronts. Look here that here a spherical wavefront of this radius. CB is the radius. The spherical wavefronts of AD is the radius. Same radius. Because this length remains same, this length remains same. They are parallel and remains parallel, and the wavefront length remains same. Generates similar spherical wavefronts like this. Equal radius. Distance between this point and this point. Distance between this point and this point. Where the light is traveling from this point to this point in the form of spherical wavefronts, it is same. When the light is traveling from this point to this point in the form of spherical wavefront remains same. Takes same time. So the distance travel will remain same in the given time. The other way, this equal radius in terms of spheres what you draw. Same distance. So in these spheres, very important, you need to understand this. There is a spherical wavefront about this point, spherical wavefront about this point. These two are points of reflection on the surface. And in this geometry, the incident wavefront, this is the incident wavefront, becomes a tangent, because the tangent to the spherical wavefront at the point C, and this tangent is in the direction perpendicular to the propagation of light like this. This is the one we need to understand carefully. The incident wavefront is the tangent to the spherical wavefronts, and at the point C, tangent to the point sphere at the point C, and this is perpendicular, the tangent is perpendicular to the ray like this, in the direction like this. There is a tangent. And the reflected wavefront is a reflected wavefront. In other words, it is a tangent to this spherical wavefront at the point D, and is perpendicular in the direction of light propagation like this. There is geometry you have drawn. Look at that, this is a tangent and tangent. Tangent and tangent. These two are equal because they remains parallel, one case. And in this geometry of drawings, these two spherical wavefronts are, what is that? Generates two triangles, that is two similar triangles. This geometry represents two similar triangles. What are them? ABC triangle. ABC, of course, right angle. This is angle between this line and this line is 90 degree. And one more triangle, ABD like this. ABD like this. This triangle is another triangle. Again, the angle between this line and this line is 90 degree. Right angle triangle. these two are similar triangles because all sides are equal. The reason here, they sharing common sides. AB is a common. So this is common for both the triangles. One side is same. And these two are, what is that? This distance is equal radius as said. Distance traveled from here to here and distance traveled from here to here in the given time, you may say. So these two distances are same. These two sides are same. And one more, these distances are also same because wavefront of same length. That is the other one. And also these two angles are same. Remaining, they are similar triangles. And remaining corresponding angles are same. The other two corresponding angles are same. If that is the case, and most important is the corresponding angles. What are the corresponding angles? The angle A, that is angle between this line and the surface. The wavefront and the surface here. And the angle between that is angle of refraction. This wavefront and the surface R. This is I, this is R. Angle A, angle B are equal. They are corresponding angles of the similar triangles are equal. It means I equals R. Angle of incidence is equals to angle of R. Even if you take the concept wave theory, it is using this kind of theoretical knowledge. With this, we prove that angle of reflection, first law of angle of reflection, that is first law of reflection, is proved by wave concept. Let us finish up. This will be next.